Hi there. I've recently been interviewed by the YouTube channel Henry AI Labs by Connor Shorten, and what follows is the resulting conversation we had about population-based methods and open-ended learning, things like that. Basically, topics of the ICML tutorial that we both saw. It's important to note that none of us is really an expert on the topic, but we are trying to make sense of it and mainly just kind of talking about the ideas. So please enjoy the conversation with Connor Shorten. Definitely check out the Henry AI Labs channel and yeah, have a good time.
Thanks for watching the Henry AI Labs Deep Learning Podcast. Today I'm joined with Yannick Kilcher. Yannick works in the data analytics lab at ETH. He has a great YouTube channel. I really enjoy watching his paper summary videos. If you like any of the videos that I'm making, you'll definitely also like checking out this channel. I'm going to put the link in the description at the end of the talk. So Yannick, thanks for doing this with me. I really appreciate it.
Thanks for having me. It's cool.
So what we're going to talk about is population-based search and a presentation at ICML that I really thought was interesting about emphasizing diversity and novelty in search. So the first question I just wanted to start by generally talking about your opinion on population-based search and the differences between population-based search and like gradient descent going straight for one solution.
Yeah, so the kind of main difference is that in population-based search, as the name implies, you maintain kind of a large population of solutions. So you don't want to limit yourself to just one trajectory. Say I start here and then I run towards my goal, but you kind of maintain a lot of hypotheses of what the solution could be, and then you kind of want to update all of them at the same time. And so there's many different variants of population-based search, but they all have this thing in common where you maintain many solutions and you kind of bet on one of them becoming a good one, basically.
Yeah, so one other thing they present their paper where they have the robot walking, and if it breaks one of its legs, for example, it can go back to the map elites table and say, okay, well, I've lost this leg, but I think maybe this solution. I wasn't too clear on how that would really be related, so I was maybe wondering if you had more insight on that.
Yes, so the context is, yeah, you want to teach a robot to walk, and the robot had 6 legs, I believe. So, and if you think of what's a solution to the problem, a solution is kind of an algorithm that takes the current sensor input and outputs how to move the motors, right? So, and if you just have like your gradient descent algorithm converging on the best solution of how to move the robot, it's just going to be like, oh, these are the sensors. Okay, I'm going to move like this, like this, like this, like this. But if one leg breaks, of course, you're lost because you only know this one way of moving. And now So you only know this one way of moving, basically, and that's it. But in population-based search, if you think of the solution as a way to move, you maintain many, many ways to move. So you basically, the objective, if you can call it like this, is algorithm, find me a lot of different ways to move, right, with my 6 legs. And now if one of my legs, I still can evaluate all of them. I still can find, okay, which one's the best. But if now one of them falls away, I have all these other solutions that I can try. Right, so then what they would do is like this leg falls away. Now they just reevaluate all of those solutions while only having 5 legs, and the best of those like is much more likely to kind of work than if you had just your single solution. So it's population based because you maintain many different ways of solving the problem.
Yes, I was also thinking about like using the search algorithms that control neural architecture search and things like that. So I was trying to think of how you might extend these ideas from the robot walking with 6 legs to the RNN controller designing the convolutional network. Like maybe I might have like more of a storage constraint or more of a latency constraint, and I could jump to a different solution like that. I'm just wondering how you think these ideas of population-based search translate into the neural architecture search, and specifically if it really is important, because like I feel like in neural architecture search you have such a direct signal with the classification accuracy. Like I don't see as much variance, I suppose, in the objective function.
Yeah, I really think this population-based approaches, they shine in multiple different areas, but one area where they shine is definitely when the environment changes. So when, something about whatever your input changes, like the robot losing a leg. So in kind of neural architecture search, you might find these methods working if you then go for, let's say, transfer learning. So you kind of train your network on one task. You want to actually do it in another task, right? And then if you maintain many solutions and you can evaluate all of them in this transfer setting, it's much more likely that one of them, is going to be fine. So, but you're right. I also believe that directly in architecture search, maybe it's not, maybe it doesn't yield that many great results. Though the other area where these methods shine, and this is with respect to algorithms like novelty search, which can be implemented as a population-based method, is they gave this really good example of deception in a search problem. So a deception would be like if you have a robot walking a maze and the robot just wants to get to the goal, right? And you would program the robot to be rewarded the closer it gets to the goal. But if like there's a wall in between and you actually need to go around the wall, then for a while you would need to move away from the goal in order to reach it. So if you have like a pure objective-driven approach, you just go straight to the goal, you would always get stuck at the wall. But if you then kind of do what is called a novelty search, where you basically reward the robot for things it has never done before, it would actually find its way around the wall. So you can maintain population of solutions that all kind of explore the space. And that in neural architecture search, maybe it's of a benefit that actually, if I probably always benefit from like adding more layers or neurons or something like this, but maybe I actually want to prune some stuff first and then add some more stuff. So I maybe want to get worse first before I can get even better, right? So it's a region where I can imagine that happening, but I don't know.
Yeah, I was thinking the changing environment. I definitely think like when you deploy a model and then you're getting new data, that you could frame that as a changing environment. And then also I was thinking about like in the context of GANs, which is something that I think is really interesting, that the discriminator classifying the the generator samples, it's a changing environment because of the generator's updates. So maybe having some kind of population-based GAN or discriminator model might help it avoid that like continual learning problem, I guess, is sort of an.
Yeah, that might very well be. There are approaches to GANs, I believe, where you have like many discriminators, and each one kind of only has its own limited view on the data, and you're trying to kind of fool all of them at the same time. But it's not the same thing. But yes, I think that might make sense.
Yeah, I've seen that multiple discriminator model too. I think that's really interesting as well. So then one other thing I was curious about is this idea of goal switching and how that might relate to the like AutoML on our existing, more like heavily studied things like classification, localization, semantic segmentation. Like, how do you think goal switching could be important? Like one idea I had is maybe if you've got like multi-class classification and it's got like a really low false positive rate or something on like one class, you might say, well, you've somehow learned a decision boundary on that class. Or do you think that wouldn't generalize and that there's no sense in goal switching in like a multi-class classification problem?
So, yeah, in general, well, when you think of goal switching in general, how they introduced it was also in the context of like this population-based search of these map elites. Maybe it's kind of So what map elites, the algorithm, does basically is it says, okay, I have a number of dimensions that I could solve the problem on. And they introduced, okay, let's take life on Earth needs to, whatever, survive. So I can either be like a super tall creature, right, to reach food that no one else can reach. I could be a super fast creature, right, to kind of run away from everything. Or I can be a super heavy creature so that no one can attack me. And so these are kind of the dimensions that you can solve the problem of reproduction and survival. And within, so what map elites does, it would segment this area, so let's say size and speed, it would segment this into a grid, and then in each grid it would kind of maintain the best solution so far that is within that grid. And then what they see is when they then kind of evolve this over time and improve each grid, is that inventions, let's say inventions, algorithm discoveries in one grid, say for a very fast creature, they would then kind of be adapted to the very, let's say, the very heavy creatures. So like a fast creature kind of discovers, oh, longer legs make me even faster. Maybe the longer legs can then be combined in the heavy creature to do something else. So this kind of goal switching, it's, think of like feathers being first kind of developed or evolved for warmth, for temperature regulation, then being goal switched over to adapted for flight. So in terms of multi-class classification, I guess it's a bit of a different problem if you just have one classifier. You can definitely make the argument that since you're learning maybe to classify one class really well, have a low false positive rate, you have learned very good features for that class. And if some other class kind of like a zebra is a horse with stripes, and then the horse is a horse but with the feature stripes being really low, you can probably classify that better or something. I'm making stuff up here, but it's a bit of a different context, I feel. If you have a single classifier, do multi-class classification, but definitely the logic applies in the feature space, I would say, where you learn features for one class and they might become useful for another class.
Yeah, I had this other thought sort of when you're discussing that, is like, what about like multitask learning? Like maybe my intermediate features get mapped to a classifier, get mapped to a segmentation, get mapped to a GAN. Like, could goal switching improve multitask learning?
Yeah, I would definitely say so. I think that's exactly what we're seeing when you look at, for example, pre-training. So if you think of like these newest big language models like BERT or something, they're really good at tasks. I don't know what it was, an NLP task. Labeling of sentiment classification is the classic, right?
That's the popular one.
I don't even know if they evaluate on that because it's so easy. But let's say BERT is really good at sentiment classification. But if you were just to train it outright on sentiment classification, it's probably not going to work because there's just too little signal. But then what happens is you pre-train it as a language model, as this masked language model, and it kind of gets really good at simply comprehending language. And that skill can then be kind of adapted over into the sentiment classification realm. So I think if you look at something like pre-training or multitask, as you say, then definitely the addition of a task might give rise to certain features that then all of a sudden can be adapted by another task, whereas if you just trained the latter task by itself, that maybe would have been too difficult. So there's definitely an analogy.
So then what I think about is, so I'm going from my pre-trained language model into sentiment classification, and maybe I also add like question answering, document summarization, named entity, like this like vector of tasks that it can go do. I'm then curious, like, when you're goal switching, it's like, how do you then combine the features later on? Or do you just like take it as, if I need this task, I'll go to this model? Like, yeah.
Well, the question here is, whether or not you implement this as a single model and kind of refer to the goal switching of features within that model, or whether you also do this now as a population-based method where basically you maintain different neural networks for different combination of these tasks. Then you'd actually need a method to kind of combine and reproduce the neural networks themselves, which I see that's going to be a bit of a difficult task, to do like some cross distillation or something crazy. I don't know how that will work exactly.
Yeah, I just wonder about two things. It's like, for my population-based search, could you have like the weights be the population, like different sets of weights, or would it necessarily need to be like taking apart the layers and designing new internal like cells, as in the architecture search? Like, because if I just have the weights, maybe I could treat the diversity search or goal switching as like stochastic weight averaging and just like mesh them all together when I'm finished with my goal switching at the end. But if it's, yeah.
It'd definitely be, if you wanted to implement your multitask tasking as a population-based approach, where it would definitely give you an easier time if you keep the architecture of your neural networks the same and simply have different weights. And then you could indeed consider something like weight averaging, or I guess a more modern approach will be like a distillation from the two teacher models into one child model. It's actually a good metaphor for reproduction, kind of a distillation from multiple teacher models. Don't know if anyone's done that yet, but I guess that might be the way to do it. If you also maintain different architectures for different problems, that might be a bit of a
Yeah, that's an interesting thing too. If you have the goal switching and then you distill it all into one model, that is sort of.
Yes. Well, if you think of map elites, right, you'd simply distill it into the appropriate. I don't even know what the axis would be. Probably, I can imagine. Okay, you have like 3 tasks, so you have 3 axes, and then you'd mix the task maybe in accordance on how far up of these axes you are, or something like this. Could be. It's not exactly map elites because your actual objectives are on the axis, but I don't know.
Yeah, it's pretty cool. So just to backtrack one step, I want to talk about like diversity-centric search, novelty. Like when I was thinking about that, I was like, can't you just initialize it such that it has maximum diversity? Like, can't you just initialize the population such that they're all like uniformly spaced and then search locally from there? I just wonder what you think on that and how this is different from that.
So, yeah, in these diversity search algorithms, basically what you're doing is your only goal is, or your main goal, depends on the algorithm, but let's say your only goal is to find diverse behaviors or diverse solutions, diverse whatever. I think the main problem with that is that the search space is so extremely large that you're going to have a hard time even defining what a kind of a uniform distribution is, because it's such a high dimensional space that even if you sample uniformly, it's almost empty. Like you're almost right. You're not getting anywhere because you have a finite computer. You need to implement an algorithm. Even if my computer can hold 100,000 different members of a population in high dimensions, that is nothing, right? So to me, the initialization might be definitely important, but I don't think you'll get around some sort of iterative procedure and getting around weeding out things such that you have space for interesting things. Because ultimately what you want to find is something interesting. In the robot maze example, the novelty search basically is, here's a robot, you start it, right? And then you want to do something that you haven't done yet, right? So if the robot crashes into a wall the first time, that's a good thing. You say, oh, cool, you haven't done that yet. But if it crashes into the wall the second time, you're like, oh, you've done that already, right? So you basically need a measure of saying how close two behaviors are. But if the robot has crashed into every wall once, the only thing it can do if it wants to do something new is actually go around the wall. And then you're like, oh, cool, you've done something new. But the space of behaviors often is so large that you can't simply enumerate all the behaviors. So I think that's the main problem, why you can't just make it diverse from the beginning.
Yeah, when I was thinking about that, I was thinking that maybe the like reward function, if you're like navigating the maze, it needs to be more refined. So like if it crashes into the wall, that needs to be like, I don't know, +3, some like unique signal, I feel like, in order to create that kind of, because like thinking of if it's just like reward 0 everywhere, but 1 if you hit that finish line, and then maybe some kind of like discounting for how long it takes you to get there. It's like I don't see how it could interpret that it's done a new behavior if all it has is it. So
Yeah.
to me, it feels like it's all about the design of the reward space now to implement such a thing.
Yes, absolutely. So the definitely, if you wanted to do novelty search, you would need to implement a measure of how close two behaviors are. So there's no way around it. And I think that's kind of crux of this method, is that by specifying how close two behaviors are, so what constitutes novelty and what doesn't, you already implicitly kind of telling the robot something about the nature of the world. So I think that the objective, because they now say, oh, we don't give the robot the objective of reaching the target, we simply give it the objective of not doing the same thing twice. I think the kind of objective sneaks in the like, again, through the specification of how close are two behaviors. But definitely this is just kind of a really simple example. What they want to say is that these methods really become important when you have ambitious objectives, right? In the maze, we can all agree, if we just design the reward, crashing walls bad, you don't have to actually go straight to the goal. You can, but go around walls good, and so on. Then it's easy, right? But in really ambitious objectives, like, I don't know, reaching the moon in the 1960s, designing general AI, curing cancer, and so on, we don't actually know how to design the reward, right? Because we don't know which steps need to be fulfilled in order to fly to the moon. I guess now we do in hindsight, right? But you couldn't have predicted. We don't know which steps need to be discovered in order to cure cancer. And it's very, very probable, if you look at history, that the fundamental discoveries that lead to us curing cancer will not directly come from cancer research. That's their entire point, right? It's not like you can have a goal, go straight towards it. If it's like a really ambitious goal, very probably the solutions will come in part from extremely non-related fields. And you kind of have to make advances everywhere, and in order to solve that problem. So the question of it's all about designing the reward, yes, but we would have to know how the reward must look. And in these really ambitious objectives, we don't. And that's where they argue, well, the best thing actually you can do is to just explore and to just find interesting things along the way, and you kind of hope that these interesting things will come. No, the interesting things will combine to form new interesting things, right? But you just don't know where you're going to end up, right?
Yes, I guess maybe you could just keep the trajectory of states and use that as your signal of novelty. But then I think like if you've got like a robotic arm with like X degrees of freedom, it's like the state space would be too infinite to really like say, oh, well, this was a significantly different sequential procedure of states and this other thing. So then the next thing,
Yes.
yes, I think this is a good transition into their pick breeder experiment. And so anyone who listens to this who hasn't watched their talk, the pick breeder is like they've got these generator neural networks with sets of weights, and they have like humans go on and they pick two of the generated images to blend together and derive a new image. And so this repeats on and on until it goes from like just like a spiral pattern into like a skull face drawing or a butterfly drawing or something like that. And so this idea is supposed to represent open-endedness in an environment. And it just generally, I just found it to be really interesting. I think it's one of the things in their talk that you look at it and you're like, oh, that's interesting. What is going on here? But it's like the mutation is really guided by the human search, which is so complex, I feel like. I was just wondering what you thought of that pick breeder experiment.
Yeah, it's really cool, and it's actually the basis for their entire book. So I've read the book, the like Greatness Cannot Be Planned, I believe. I forgot the title. I'll link
Yeah, I see.
yeah.
Yeah,
But so that this they kind of start out with this as a motivational example of what if the only goal is to do something interesting, and without any objective. So all you do is kind of choose slight variations on a current picture, and you see what you end up with. And I thought it illustrates their points extremely well. So it illustrates, for example, goal switching. Is that so if you were done with your sequence of image manipulations, you could then save it into the database and someone else could pick up from it and then kind of continue it. And since every human finds slightly different things interesting, right? You could take someone else's final result and say, that kind of looks weird, but then your modifications to it will be different than that human continued breeding the picture. So what you end up is, and they show this, for example, one picture ends up being a car, and it had been adapted from an alien face, where the eyes of the alien face became the wheels of the car. And so the first person might have been like, oh, this looks more and more like an alien face. I'm gonna make it more like an alien face. And then the second person is like, oh, that kind of looks nice. I'm gonna modify it in a different. So they basically give this example of, if you have an ambitious goal like getting to a car just from these very simple picture generation networks, then the stepping stones to get there have nothing to do with cars, and the people that did it didn't have a car in mind while going there. And the second thing is that if you try to get a car from the beginning, I believe they've done this. If you try to, you can't. Like, it's just the sequence of things that you have to go through is so complicated and convoluted that if you were to try to end up with a result, it's basically impossible. So these kind of illustrate their points very, very nicely. And it's a cool experiment in itself, but they use it kind of as a basis metaphor for then going on, jumping off.
Yeah, I just think it's so interesting, this idea that it's like you can't design a car unless you don't try it, unless you just happen to come across that. It's sort of like, I think about like if I was to fire up GarageBand and start trying to make a song, it's like I don't know exactly what it's going to sound like. I'm just going to kind of explore until I come across something. So then I was thinking about like with the GANs and the way that the GANs design images. Like, so this is like sort of a design I drew up that I'm curious what you think of. It's like, what if the generator just like tries to make some object, and then a pre-trained classifier says, oh, I think it looks like this maybe, and then you send it to like a refining network. So the GAN just sort of searches for objects, and then some classifiers are like, oh, I think it looks like, sort of like how the pick breeder, sort of like how we're like, oh, I think this looks like a skull or whatever. So I'm going to try to, refine it now. Do you think that would be an interesting thing, or?
So you'd have like a two-stage process. First, you do something general, and then it gets classified, and then you'd have like a special generator just for the skull class and the special discriminator just for that. Yeah, I don't see why not. Might be hard. It might be hard to get the first generator to be sufficiently diverse. So you might need some kind of discriminator signal even at the beginning.
So then
Yes,
does
but
that,
I mean,
yeah, like how do you think the pick breeder experiment could become fully automated such that there's no human in the loop?
yeah, that's a thought I had as well, because to me it seems that the kind of course the resulting pictures, the fact that they look like human objects or recognizable objects, is a result from them being bred by humans. Like the fact that it looks like a car or a skull or something like this is very much. But also, I guess that could be abstracted in we just not expect the results to be like human recognizable objects, but maybe something else. The much more deeper construction in Pick Breeder is the fact that the measure of interestingness is provided by the humans, right? So the humans, they click on a picture and then they get variants of that picture and they click on the one that they most like. This sense of interestingness of I like this one. That's the fundamental core that's provided by the humans as an input to the system. That's what drives the entire thing. It's exactly the same as before. It's when you teach the robot which two behaviors are close enough, like, oh no, that's too close to before, that's not novel, or yes, that's sufficiently different than before, that is novel, right? This sense is somehow, you either need to specify it or you need to have the human in the loop to provide it. I feel it's very, very hard to capture that in an algorithm as of today.
Yeah, like something I think about is like maybe I'd have like my 1,000 class ImageNet classifier, and then maybe I'd have like a style classifier, like a neural style transfer network that I've like chopped off at like some intermediate feature. I'm going to take that as my style, and so maybe I'm like classifying. I think it's like an airplane, and then I kind of like this style for it. That's sort of like how I would think about trying to automate that. Like I don't know. I guess like I don't know if I guess it's interesting, but I also feel like when you're doing the pick breeder, you're kind of like, oh, I'm gonna try it now. Now that I see this vision, I'm gonna try to make it like look like that now, I suppose. Like
Yeah,
I think
yeah.
yeah. Like I
So
think I could mold this into a skull, and then you start doing that.
yes.
Yeah.
Yes, they're very much so. They're not advocating random exploration. What they're advocating is basically, if you have an ambitious goal, then you basically don't know the stepping stones. But from stepping stone to stepping stone, that's where objectives are very handy. So when you want to say, this already kind of looks like something, I want to make it more like that. I want to make it more into a skull, right? It already has like two circles and kind of the shape, but I'm going to drive it there. That can be very objective driven. But in the grand scheme of things, you don't know. Then once you have the skull, right, someone else can develop that into an even new thing. So, yeah, indeed, if you are in kind of a local search in this space, then an objective-driven behavior, like what you're saying, like I want to make it as much this as possible. That's actually a thing they're advocating for. But then from their end result, yeah, you would need to then restart again, do the same thing with like something else.
Huh. Yeah, it's really interesting. I just thinking about I'm thinking about like the stepping stones and like is how would you define the space of stepping stones to to any kind of thing? I guess it's like you could still design some kind of, maybe it's discrete or maybe you have some kind of signal you can get back from it. and I guess it's just a lot to think about. I don't have any direct takeaway
Yeah.
from it.
They give this great analogy. I feel like if you have a really ambitious objective, it's like crossing a lake, but the lake is covered in fog, so you basically can't really see very far, but you can always kind of see the next stepping stones, right? And you can then try to go from stepping stone to stepping stone, but you don't know which one to take. If there's like a fork and there's two ways possible, you don't know which one, right? So all you can do is basically go the most interesting one. And they relate this to scientific research. So yeah, if we want to accomplish some really great research goal like artificial general intelligence, we don't know, but we can see the next stepping stones, right? We can see, oh, from what we have right now, what interesting combination could we make that still kind of makes, that's not total garbage, right? So in the local search, I can try to say, I want to do this. I want to do multiple generators and it's multi-stage, and then this thing, right? This is kind of a stepping stone, and maybe that will then lead to something more interesting, and so on. So yeah, that's kind of how they relate. I like this metaphor of the lake.
Yeah. I just like, could like a meta controller try to put the stones down, and then the objective is like, or is the space too enormous that idea of having a meta controller guide the stepping stone placement is just like absurd, and there's no way that would work. That's sort of where I'm thinking with this now, is like,
So they actually, that's exactly the question, right? Of what I believe you need such a meta whatever. Because the space is too large, you somehow need a way to choose the stepping stones in the first place, right? You somehow need a way to do this. Now, what they're saying is that if your goal is really ambitious, then a meta controller that simply wants to reach the goal is bad, because what we discussed before, you might need a lot of inventions from other fields in order to make goal happen. And if you simply go your field, maximum power towards your goal, that's not going to happen. Now, if your meta controller is actually just something that wants to produce interesting things, then that's actually something they advocate for. That is exactly what their algorithms are trying to capture. They're trying to capture locally, yeah, we want to get better at a particular thing. What those particular things are and the order of these, that should be novelty driven instead of goal driven.
Yeah. The interesting component. I guess I'm sort of biased towards liking the objective design, and now I'm thinking like, okay, well, let's abstract those meta controllers one level up and have a meta controller, and just repeat this until the hierarchy makes sense. But
and that if you're a bit cynical, that is what you will also hear out of, and they have to argue in their book a lot against that. Like, isn't the implementation of a meta controller that just searches for novelty in itself an objective again? And then they give some good reasons why actually it is different. It's more like a constraint on your search. If you think of natural evolution, for example, it doesn't really have an objective. And if you think reproduction and survival is the objective of natural evolution, it doesn't really. The good reason they give is the objective has already been fulfilled by the very first organism to ever live, right? Why didn't it stop there? Right? Why didn't it stop very first cell? Okay, done. We've fulfilled the objective, right? It's more of an actually a constrained optimization, where the constraint is you need to be able to survive. That's kind of the minimum bar to being on this planet. And then, well, I'm saying constrained optimization, but it's not an optimization. It's more of like a constrained search. Yeah.
Okay, yeah, I think. Yeah, I guess it's just like, I definitely think I'm closed in this world of trying to think of these constrained problems, and I haven't really like thought more generally about just like exploration as a whole. But anyway, so I just wanted to ask you generally, like, you're a deep learning researcher. I want to ask, like, what areas of deep learning are you really interested in right now, and what do you think is promising in the near future?
So I'm currently working in adversarial examples. That is a really interesting topic. There's lots of questions still open, but I'm generally interested in pretty much anything that is not. I'm not too interested in like the newest fine technique on getting the latest state-of-the-art numbers. Even though that's probably super important for practitioners, I'm basically agreeing more with the authors of this tutorial that let's just try to do interesting things. And to me, these areas in terms of open-ended search, open-ended learning are very interesting. I think reinforcement learning still has a long way to go. I think actually NLP still has a long way to go because I don't believe the current models are the end of it. So I think it's a really exciting time. And
Yeah, I love thinking about adversarial examples because it definitely flips the CNN idea on its head. And then I had one other thing about adversarial examples that I'm interested in is there was like an interview with Elon Musk and this Lex Friedman researcher where he asked him about adversarial examples on his self-driving cars, and he seems dismissive of it. He says he thinks basically you could just average different patches of like test time augmentation to overcome adversarial examples. So like in your research, do you think that like the example where they add the noise mask to the Panda and they're like, oh, it's a given now, if they just perturbed it like 9 more times, do you think the prediction would average out to Panda still?
That is a very difficult question, and from experience, simply adding noise and then feeding it to the classifier, even if you average after that, usually will defend against adversarial examples to a point, but it will also degrade your classification performance. Because maybe I understood it wrong, but my understanding is I have my input, right? And I simply add noise to it and then feed it through the network. And I could do this many times, right? And then average the prediction. But usually this will help against adversarial examples, but it will also degrade the accuracy of that classifier. So it might actually make your self-driving car worse in the overall, because how often is it going to be attacked against a adversarial example? Like it's going to be attacked maybe, I don't know, once or twice a year, maybe if it drives by some hacker's house, right? That puts some sticker on a stop sign or something. But the rest of the time, I would actually like to retain the best possible classifier. And if I always have to add noise, then that's not possible. So the research we're doing is actually into the direction of can we retain the original accuracy while still kind of detecting these samples. You somehow have to get a trade-off somewhere, but just adding noise isn't the final solution yet.
Oh, so with these adversarial examples, they're only going to make misclassifications like that if it really is adversarially sought after. It's not just like the noise perturbation would be such an enormous base to find it otherwise. Is that?
Yes, you really need to try. So it's very unlikely that some random thing. Of course, these networks can be confused by random noise, but that is, I think one of the self-driving cars once drove into a big white truck because it was large and white, so it thought it was sky. But other than these failures, yeah, you really have to try to find an adversarial example.
Really cool. Yannick, thanks so much for doing this. Anybody watching and listening, definitely check out Yannick's YouTube channel. He has really great paper summaries and all sorts of things. Thank you.
Hey, thanks so much for having me.